Hello and welcome back, everybody. I'm calling this section Indexing, Sequences, and Functions. You may be quite confused by why I'm including functions again. We already covered functions with sets and maps. We have a different perspective on functions today. So in some sense, today we're talking about how functions relate to both indexing and sequences, because I think interpreted correctly, one should think about functions, sequences, and indexing as one and the same thing, at least to make your lives easy. Maybe the mathematician won't interpret it that way, but the standard applied mathematician or chemist, physicist, engineer, etc. should probably think about functions and sequences along with their indexes as the same thing. So let's just start where we would expect to start and talk about this word indexing. So let's say an index is a variable parameterized over a set. And of course, this is why sets were important in the first place. We call this set an indexing set, and I'll use the letter capital I for now, but you don't have to really use that letter at all. Maybe the variable I'll use lowercase I for index and capital I for indexing set. This is a very common way to do it. So it's a variable I parameterized over a set capital I, and I will notice really quick that I will do my best to use the I with the tail to be the imaginary number, and the I without a tail to be an index. But we can also use M, N, K, J, L, etc. for indices, plural of index. So there's nothing too special about using the variable I. But what is it? An index is a variable parameterized over a set which is associated to a collection of mathematical objects themselves dependent on I, so dependent on the index. Now that's pretty vague. If I make an example, we can make this a lot less vague. So let's get an example. So let's say when I as an element of this indexing set, and suppose the indexing set is the set 1, 2, 3, then I can take these values so you can take the values 1, 2, and possibly 3, and there's another collection of mathematical objects that are associated to this index. So the example is I is in the indexing set 1, 2, 3, along with, say, something like V sub I, where V sub 1 equals 7, V sub 2 equals -4, and V sub 3 equals 5. Then we can say the set V sub I in I is an indexed set. So basically, this collection, also known as a set, is going to be dependent on the index I. So whatever that index happens to be, it'll help us define a set. And we often use, this isn't necessarily always true, but I'll make it as a remark here. We often use a subscript or superscript to denote an indexed object. Okay, so these were the examples that we just saw. V sub I is indexed by I, and the set is parameterized by I. By the way, this set, because it's got that whole idea of being I and I there, this set is actually equal to V1, V2, V3. And we know the values of V1, V2, and V3 are 7, -4, and 5. And so this is just an efficient way of describing larger sets dependent on smaller sets. So in fact, this almost feels like set builder notation, but it gives us a different way of thinking about kind of set builder notation. So let's look at quite a few more examples. This doesn't make sense until we make more examples. Let's do something like x sub n. So this is Now, the variable x indexed by n, and let's say that x sub n is equal to 2n plus 1. And the indexing set that n exists in is 1, 2, 3, 4, dot, 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 is precisely the natural numbers. So now let's look at the set. Observe we have the set x sub n, n is in these natural numbers, and that set is allowed to be equal to 2n plus 1, n in the natural numbers. And you can also explicitly construct this as, well, plugging in n equal 1, we get 2 times 1 plus 1 is 3, n equals 2, we get 2 times 2 plus 1 is 5, 7, 9, and so on. These are the odd numbers, except 1. And so indexing kind of gives us a new version of set builder notation. Let's look at one more brief example. Let's do something like f sub x equals x squared minus 2. This is now the variable f indexed by x. And then we'll specify that we say, and x is in R. Now what we can say is that we have the set f sub x, x is in R, which happens to be equal to x squared minus 2 when x is in R. And this, you can't really write it out as a nice collection of objects like that because there are infinitely many x's and r's, so you can't really make it clear what that set looks like until you decide that you want to plot this. Note on the plot, x squared minus 2 looks like this. And so if we look at the output, this is basically looking at the range of the function, where on the y-axis is being hit. Well, every number above y equals negative 2 is being hit. So in fact, this is going to end up being the interval, closed interval, negative 2 out to infinity open on the other end. So all of a sudden we have this very strange notation of saying f sub x equals x squared minus 2. It's kind of this set where it's parameterized by x and r. And it turns out that if you combine all of the entries of that set together, you just get that interval, negative 2 to infinity. Now indexing is a little bit stronger than just building sets. And I'll mention why here. So indexing is stronger than building sets because a description of the form x squared minus 2 x in R represents a function. And I think everybody agrees that it represents a function. You were probably all recognizing that from the beginning, that it represents a function. And in fact, the function, where the domain is the indexing set, R, right? Because R right here is my indexing set, that's going to be the domain. And the range is the set produced under the indexing. Maybe I'll say under computing the indexing. So the range would be everything when you include all of the x's in R. And that's what we found in this case. The range was the set that I wrote up top there, negative 2 to infinity. And so you get this very condensed notation of functions, domains, and ranges all together. And we also have the ability, right? We have the ability from up above here to work with, objects like x sub n, 2n plus 1, where it looks like our range is completely discrete. You can tell that the domain is discrete as well. And you just gain so much more information. Really, indexing is a very, very condensed form of notation. This is why I included functions in this section, because indexing really does prepare us for functions. Let's see an example of an object indexed by 2 variables. So we can grab something like m sub I and superscript j, and let's suppose this is equal to I times j minus 2 I plus j, where I and j are in the indexing set 1, 2, 3. Now, in fact, I could have made I and j in separate indexing sets, but I just decided to put them in the same indexing set here. And what we can do is we can compute this entire set, m sub I superscript j, and then we say that I and j are in the index set 1, 2, 3. So what does this set look like if I compute it? Well, let's figure out what this means. This means that we have all combinations of i's and j's in this set, which if I write it all out, that would be m11, m12, m13. And I'm gonna write this out in a very particular way now. I'm gonna jump down to the next row and say m21, m22, m23. We'll see in a couple weeks why this is a natural way to write it out when you have a double indexed collection. m31, m32, m33. So now I could compute all 9 of these if I want, and what I have to do is just be aware of what is the specific value for I and j, I and j, I and j in every single case. Well, what I know is that those values for I and j just get plugged into this formula. So if I'm going to compute all of them, which I can do, and I will do just right now, all I do is I look here and I grab I equals 1 and j equals 1, and I plug into that formula. So plugging I equals 1, j equals 1, and I have 1 minus 2 times 2, also known as 1 minus 4, I have negative 3. I can then continue with the next case. When I is 2 and j is 1, I have 2 times 1 minus 2 times 2 plus 1, so I have 2 minus 6 is negative 4. And if I go ahead and fill this out all the way, what I end up with is negative 5, negative 4, negative 4, negative 4, negative 5, negative 4, and negative 3. You could pause the video there and make sure that you know how to get each of those numbers, but this would be a nice way of describing the output of this indexed set. Now it turns out that indexing is, and I've already mentioned that indexing is stronger than building sets because it represents a function where the domain has an indexing set and the range is a set produced under the indexing, but it's also stronger in another way. So this is where sequences come into play. So sequences are indexed sets which preserve an ordering because of the indexing. So I don't know if I maybe made this clear, but as sets, something like 1, 2, 3 and 3, 1, 2 are equivalent. There's a true equality here. But as sequences, so long as I ascribe this set, so 1, 2, 3, I need to actually give it an indexing. So if this results from something like n, such that n is in the set 1, 2, 3, the moment I write it out as an indexed set, this is no longer equal to the set 3, 1, 2, because there is a new indexing here. The indexing for the set 3, 1, 2 is something like n mod 3 plus 2. Now, if you don't know what mod 3 means, don't worry about it. But if you do, you can verify as well that this would be equal to n mod 3 plus 2. But it's because, right, these are not equal. These are very distinct objects. And the idea of these as sequences see the objects over here. So sequences kind of give us a little bit more power to distinguish two sets from each other because all of a sudden we care about order. And I will mention that much of the time. So remark, 99% of the time, the indexing set of a sequence is the natural numbers or a subset of the natural numbers. So what you'll see actually a lot of times if you took a regular Calculus 2 course, sequences are just defined as indexed sets, where the indexing set is the natural number n. But in reality, you can form sequences other ways, but this would be the most common, and then you just have something like where a sub n is equal to n divided by n plus 1, and then hence the set, or the image of the sequence, would be a1, a2, a3, and so on, also known as 1 divided by 1 plus 1, okay, 1/2, 2 divided by 2 plus 1, 2/3, 3 divided by 3 plus 1, 3/4, 4/5, and so on. And written as decimals, this is 0.5, 0.6, repeating, 0.75, 0.8, and so on. And the nice thing about sequences, when they have an indexing set which is infinite, suppose one-dimensional and infinite, is sequences can have limits. So since there's an ordering to a sequence, you have a notion of limits because you can just move forward in the ordering, and that's going to give you your limit. So for example, in this case, it looks like a sub n is approaching 1, because the next term, 5, 6, would be like, what, 0.833 repeating, and then 6/7, 7/8, and so on. You just get higher and higher and closer to 1. So you have a notion of limits, and notions of limits are incredibly powerful in math. Limits, let's recall, limits give us calculus, and so much more. So in some ways, sequences are kind of the objects that we should always be thinking about, so long as we have the ability to think about them, because we can associate limits to them. And let's just look at one other situation of a sequence. Here's f of x, which is a sequence parameterized by x in R, where f of x individually is equal to x divided by 2x plus 2. This can be written out as a function, can be interpreted as a function. And technically this should be x in R. X is not equal to -1, because you do have an asymptote at -1. But what does this function look like? It kind of goes like this, and then like that. You've got this nice asymptote at x equals -1, and then it comes back around over here, where this is the value y equals 1/2, and this is the value y equals 1/2. So that's what the function looks like, but once again, we want to think about this. If we think about it as a sequence, it's really, in some ways, just the collection of points that has an ordering, right? It's each of these points, maybe start at 0, but each one has an ordering, and we're just looking at the y values here, actually, but we're ordered to the right. And so f of x has a limit. It approaches 1/2 as x approaches infinity, interpreted as a sequence. Now, like I said before, most sequences, we're going to think about the indexing set as n, and so this later case won't be nearly as common, but it's nice to keep in mind that like the functions that we naturally interpret are actually sequences as well. Okay, so I'm going to stop class there today. We'll get a lot more practice in the applications video, which is coming up next. I'll see you then. Bye.